Okay, so we're looking at kinetic molecular theory, and like all theories, it's like a representation of what's real, but it turns out it's very accurate. Okay, so like when we say gas molecules are always in motion, they're always mowing.
This is 11, actually, isn't it? Instead of 10?
I think it's the end of 10. No.
Or is it 11? Oh, it's 11, huh? 11. Sorry, my bad. They're always moving, constant motion. The other thing is gas molecules in kinetic molecular theory have very little attraction for each other. So we tend to say no intermolecular attractions or no attractions to each other. I'll write those both things out. So no attractions between gas molecules. Oops. We call those intermolecular forces. So inter, that means between, molecular forces. It's actually kind of what was supposed to be talked about in the very end of chapter 10 and section 8. We only covered the very basics, dipole, but this whole thing about molecules, just to make it real simple, the reason all of these are gases, all the noble gases are gases, is because they don't have any attractions for other gas molecules. So if you take helium, right, helium atoms aren't attracted to other helium atoms, and so they stay in the gas phase. If they had a strong attraction for each other, what would they do?
Solidify.
They would solidify or become a liquid, right? So if you look at water, that tells you something about water. The molecules of water have really strong attractions for each other, and that's why for the most part when we see it at room temperature, it's a liquid state rather than a gas state, because the molecules have pulled themselves together. They also release all that energy as heat when that happens. Another side story. But for example, chlorine, fluorine, oxygen, and nitrogen, right? The diatomics, right?
Yes.
These guys are all gases at room temperature. That's why they're, you see the ones that are red on this periodic table? These are the ones that are gases at room temperature. But there's lots of
Go against that?
What's that?
Doesn't the diatomics go against that?
No, because
See what I'm
the
saying?
bond is an intramolecular. It's between atoms of the same molecule. Intermolecular means like N2 isn't attracted to another N2.
Okay.
That make sense?
Well, kind of, except that that kind of says that, I mean, it just seemed like the diatomic, you know, the two nitrogen, the two oxygen and stuff contradict what that says. That no attraction between gas molecules.
Right, there's attractions within the gas molecules. That's why you get
Atoms, not
N2.
molecules.
Yeah,
Excuse me.
yeah. It's inter versus intra. So we have two terms. So inter is what we're working on here. Okay, so the other thing is when we talk about kinetic molecular theory, and this works out pretty well, there's a lot of space between the molecules. Right, gases, right, their size is small compared to the space between them.
They're really spread out.
Yeah. And so, yeah, the way we think about it, if you think about it in general terms, there's just spread out. There's a lot of space in between. It's sort of like the planets in the solar system, if you kind of know that comparison well. There's almost nothing in outer space. That's why they call it space. And there's planets, but the space between the planets is huge. So as big as Jupiter is, right? Can we see Jupiter from the Earth?
Yes.
But barely, right? So but yeah, so it's a planet, but the size of Jupiter is huge. It's almost like a second sun. But it's so much distance between the planets, you can't see those things. It'd be cool if you could, but you can't. So, oh, the last thing that I was going to mention, maybe I should mention one other thing here, but because there are no attractions between the gas molecules, okay, they always move in straight lines. mention two other things since I'm going down this path anyways. And because there's no attraction of gas molecules for each other, when they hit each other, they bounce off each other elastically. Okay? You know what an elastic bounce is? Like a super ball, when you drop a super ball, if it bounces up to this high again, like if you let it go from here, it bounces up to this high, that's an elastic collision. It ran into the floor, and all the energy that it had going in that direction got transferred coming back. And so we generally say that the collisions are elastic. I'm going to put it right there because there's no room for it. So, always moving, no attractions between the gas molecules. The consequence of there's no attractions is that they have elastic collisions and they always move in straight lines, so it kind of falls out of that. If they had attractions for each other, like, I won't go that way. If there's two things that are attracted to each other and they run into each other and they're attracted, right, they stick, right? And they lose some of their collision force because they're stuck together because you've got to pull them apart now. So that's kind of the idea. All right. So that sort of defines kinetic molecular theory. These make up, sorry, let me do this. When you have something that has all of these properties, it's called an ideal gas. Most gases behave that way at room temperature. Okay? Most of them behave as ideal gases. So let's talk a little bit. One of the key things that we think about when we talk about gases is we talk about pressure. And there's really, okay, well, what's pressure? Somebody explain to me what pressure is in their own concept. It's a force, right? Can push, right? So the real definition of pressure, okay? And then I'll explain to you why it's this way. Pressure is a force per unit area. Force per unit area. So like if I were to stomp, so I have big feet, okay? And I weigh a lot, but ignore that part. If I were to stomp on your foot with my tennis shoe on, that would hurt, right? Now imagine me in high heels. Don't, but I mean, imagine if I stomped on your foot with a high heel shoe. Okay, now you got to get that picture out of your head. What would happen when I stepped on, like a stiletto heel? Huh? That would hurt a lot more, right?
There's more pressure in that spot.
Yeah, because when I stomp on your foot with my foot, I don't wear heels. I'm short enough, maybe I should, but my foot's really big. And so all that force, even though there's a lot of force when I do this on your foot, it's spread out over the area of my heel. But if you take that area and you decrease it to like the size of a stiletto heel, there's like 100 times less area. Because remember, areas are square units, right? And so what's going to happen? The force will be the same, but the pressure will be 100 times higher. Okay? So you can literally, self-defense thing, if you're wearing a heel, somebody comes up behind you, if you jab down with your heel really hard, if you're wearing a heel, you can go through their foot. That's cool. Yeah. Yeah, so I just encourage you actually not to wear heels and be aware of where you're at, because heels are really hard. It looks like they're really hard on your feet and your calves, but I don't know. That's just me. I'm an old guy, so what am I doing? Yeah, so force divided by an area. Okay, so it turns out for gases, pressure depends really on a bunch of different parameters, but we often think of volume and moles. Like how much gas is in a container. Moles is like the number of molecules, right? And the volume defines the surface area that those molecules are bouncing off of, right? So there's one other thing. I didn't put it up here. I'll put it up in a second. There's one other thing. But if you think about a container, like a balloon, and I almost always think about like balloons when I do this kind of stuff. and you have a gas in here, right? The more, and you guys know this, the more molecules you have on the inside, right, the more that's going to push out. But if I don't allow the surface to expand, then the pressure goes up. Okay? It's like blowing in a soda bottle. Take a soda bottle, and you can blow a little in there, and then as soon as you get a little bit in there, it's almost impossible to get any more. And that's because the pressure's gone up because you've put more moles of gas in there. The other thing is, too, though, if you take the same amount of molecules and you put them in a really small container, now you have all these gas molecules on the inside that are pushing on the walls, and so the pressure is going to be higher there, too. There's one other general factor that affects pressure. Anybody know what it is? Temperature. Temperature is the other. Oh, yeah, sorry. Down here. Temperature. So if the volume, okay, let's do this. If the temperature goes up, like let's say the soda can was sealed, and then I heated it up, what would happen to the pressure on the inside? It goes up, right? You know this because have you ever left one in a car in Central Valley? What happens? It blows up. Yeah. Part of it is you have carbonic acid in here, and so the carbonic acid, it's not as soluble in high temperature, and so it comes out, and eventually it just blows the lid out. I had a whole case of Diet Dr. Peppers I think I bought on sale one time, and I put them in the back of my wife's car, and she didn't know they were back there, because she likes Diet Dr. Pepper. And then before you know it, like half of them, all the lids were like pushed out, and a bunch of them started leaking, but none of them really exploded until we got them out of the car and one hit the ground. And then okay. It also happens when you freeze it. I heard you say that. When you freeze it, you can...
Isn't that imploding though?
Huh?
Isn't that causing to implode?
No. It's because we haven't talked about it, but when ice forms from water, it expands. And the force of expansion is huge. It's really big. Okay.
Pulls the mountains down.
Yeah, it does. But over time. So temperature is one thing for sure. Moles is another thing because you put more gas in. So moles goes up, pressure goes up. Temperature goes up, pressure goes up. Volume gets bigger, pressure goes down. Yeah, so and we're going to talk about proportionalities, but volume, when volume goes up, pressure goes down. And if the other way, if moles goes up, pressure goes up. And if temperature goes up, pressure goes up. And I didn't say it before. I should have said it probably very clearly. The force is created by lots of gas molecules bouncing off the wall. Now you can't see them, but literally think if you thought of yourself as a gas molecule and you're running towards a wall and you run into the wall, what happens? A lot of force, right? You push the wall with your weight and then you bounce off. That's what the gas molecules are doing. But because there's no intermolecular attractions and they're not really squishy like we are, they bounce off with just as much speed as they came in with. When you do it, you're going to bounce off a little bit because you're squishy, and when you squish, that uses up some of the energy. Okay? Just a gee whiz thing. We don't do this calculation in this class. How fast, like if I had hydrogen gas at room temperature, how fast do you think it's moving when it runs into a wall? It's a pretty big number. I think it's 400. I'll have to double check.
It's a lot.
It's in the hundreds to thousands of meters per second.
I think it's 4,000, yeah.
So like if you had a gas molecule and it didn't actually run into anything, right, it would cross a football field in a fraction of a second. That's how fast they move. So even though they don't weigh very much, right, there's a lot of them in a gas container. They're moving really fast, and that's what creates the pressure. Okay, so I said pressure is affected by temperature, one of the things that you need to get used to doing, and so this is where I teach this stuff, you need to understand the Kelvin scale. You can't really quite understand it until we study some more of the gas laws. But the Kelvin scale goes from 0 Kelvin and up, and 273.15 Kelvin. And this is not an exact number, so that's 5 sig figs. It's something that they measure. Okay, 273.15 Kelvin is 0 degrees Celsius. So even though it sounds like a big number, that's what we think of as the freezing point of water, that temperature, okay? The boiling point of water is what in Celsius? 100, right? So it turns out, so this is freezing point. This is boiling. It's 373.15.
So the degrees are the same size.
Yeah, so every degree in Kelvin and every degree in Celsius or centigrade for us old people,
That's right.
it's the same size. Okay? Why magically on the Celsius scale do we have minus 273.15? Okay. This is and that's in degrees Celsius. In Kelvin, we just call it 0. Okay, and it turns out we can't actually get to 0. This is the coldest possible temperature that you can achieve anywhere. In space, in outer space, where there's nothing, it's pretty close to 0 degrees Kelvin. Yeah, pretty close, but not exactly. So why is this? Because it turns out, okay, at 0 degrees Kelvin, there's no more kinetic energy. The kinetic energy is the energy of motion. So like when you get to 0 degrees Kelvin, everything stops moving. Now things will be stuck together, so there's forces of attraction, there's potential energy there, but everything stops moving, and a lot of weird stuff happens at that point, and you'll learn about them in other classes hopefully. But that's the coldest possible temperature, so they call it absolute 0. People spend a lot of time trying to get to absolute 0. They do weird things. I could tell you about them in lab if you were curious, but they do weird things to try to get things to absolute 0. Okay. So let me scroll up. Take me a little bit to... I talked about some of volume in moles. I just want to do a couple of conversions. We'll just talk about the units of pressure. Okay, so when we measure units of pressure, the thing that there's probably 2 units you'll hear a lot. Okay, one's PSI, pounds per square inch. Where do you hear that term? Tires, right? Tire pressures. Anything you inflate has a PSI rating to it. Okay, that's pounds per square inch. So now think about this. That's about a square inch, okay? 1 atmosphere, this is the unit maybe or may not have heard, okay? But what you're feeling right now is about 1 atmosphere. You don't feel it, right? Because you're used to that pressure. That's about 14.7 pounds per square inch. So like, take a little section of my arm like that, the air pressure right there is about 14 pounds. And I don't feel that 14 pounds. It pushes from all directions, so it doesn't make my arm 14 pounds heavier. But if I had no pressure underneath my arm here, then for every square inch, it would be like 15 pounds of pressure. So on the top of my arm, it would literally be like 400 pounds of pressure pushing my arm down if there was no pressure on the bottom side to oppose it. Okay? Now that all kind of depends on how big your arm is. Like a submarine, if a submarine goes down just a little ways under the ocean, then you take every square inch, it's like 33 feet, I believe. Every square inch on the hull of that submarine is 14.7 pounds. So you go all the way down to the bottom of the ocean where some of these guys cruise at the very depths of the ocean. The pressure down there is crazy. Right? We'll talk a little bit about that as we go along. So 1 unit is this 14 14.7 pounds per square inch. Okay. The other one that you may have heard is this one up here. And the reason I say that is because that's the one that gets reported like in the newspaper when they talk about atmospheric pressure. They say, oh, the pressure's 29.92 inches today, okay? That's inches of mercury, okay? You know, mercury's a liquid, right? It's one of the two liquids on the periodic table. So we have bromine, that's one. We have mercury, that's the other. Mercury is very dense. It's about, ballparking 10, 15 times more dense than water is. So if you have 29.9 inches, that's mercury about from here to here. That's 30 inches. Okay? If you get that much mercury, and remember, every, like, in a tube, that would be 1 atmosphere pressure. Okay? Again, that 1 atmosphere of pressure is this, 14.7 pounds per square inch. So that tube, that cylinder, mercury, in terms of its mass per square inch, is about 14.7 pounds. Okay? Okay, so all of these are different units. Let's see what I want. And they all represent 1 atmosphere of pressure, what we call 1 atmosphere of pressure. We also have standard temperature and pressure, which are referred to as STP, right? Standard temperature and pressure. And for scientific purposes, STP is 1 atmosphere in 0 degrees Celsius. So when we compare like data for gases, a lot of times we convert it over to STP conditions so we can compare, like, well, what's the volume of that gas at STP? Or what's the density of this gas at STP? We often convert everything over to these conditions. In the military, it's 25 degrees, depending on what you're doing. Like, there's also standard temperature and pressure for like the human body. So you'll hear STP. It doesn't always mean the same thing. It just depends on what discipline that you're in. So for chemistry, it's 1 atmosphere, 0 degrees Celsius. 0 degrees Celsius just because, that's when water freezes. And 1 atmosphere because that's typically, right, what we're experiencing. It's 1 atmosphere. Room pressure. Now, I will add this little side thing too.
Like 25 degrees Celsius is close to room temperature too, isn't it?
Yeah, room temperature. There's a standard room temperature. And in chemistry, that's 25 degrees Celsius. Okay? So that's just something to remember. Standard temperature and pressure for gases is 1 and 0. And room temperature, when they say room temperature, is 25. I'm just about out of time, aren't I? Or do I get to go for another hour? I always forget these things. You guys can stop me,
Basically, if the pressure goes up or down, the freezing point can change.
Yeah, it's over. I'm so sad. I can't answer questions. Lecture's over. What?
If pressure goes up or down, then essentially your freezing point and boiling point will go up and down.
Yes. Mostly your boiling point changes. We'll talk about that. That's later. But if the air pressure is lower, then the boiling point is also lower. And if the air pressure is higher, the boiling point is higher. So like if you go up to Colorado, that's like a mile high.
Right.
And then you boil water, it's like 92 degrees, I think. So when you cook food, it takes a lot longer because you're not actually at a high enough temperature. Like boiling spaghetti, pasta, stuff like that.
Is that why you can't freeze when you go